All right, welcome back, everybody. Let's start checking our homework. Pause if you need to, folks at home. So hit pause here because I'm going to go on pretty quickly. All right, there we go. Here is 62. I want to do 62 a little bit different than what you see on the board. This is actually a key from a while ago. It's just a different way to do powers of I. Like what you could do is make all powers of I even. I know we talked about that whole mod 4 thing, that divisible by 4 thing. What you can also do is make all powers of I even by, if it's odd, just removing one. You know how we started that whole process of just taking like I to the 6th is really like I to the 5th times I, right? So I to the 7th is I to the 6th times I. So I to the 11th is I to the 10th times I. Why does I to the 10th help us? Well, because if it's even, well then it's really like I squared to the 5th, right? I squared to the 5th because power to a power means I multiply. And if I squared is -1, then it would be like -1 to the 5th, which is -1. So that kind of reduces it down for us. And you're always going to be left with an I or not an I in there. So here's how I would do this problem, though. I would say I'm here at I to the 11th, and I say, negative I to the 11th. And I say, okay, what about 11 divided by 4? What's the remainder? 3, right? So the remainder is 3. It's 2.75. That 0.75 means this is going to be equivalent to negative I to the 3rd. Right? What is I to the 3rd? 1I, -1, negative I, right? Just got to memorize those first 4. 1I, -1, -1, negative I. And that's I to 0, I to the 1, I to the 2, I to the 3. I said that really weird. So it's negative I. So negative I, so just positive I in the end. That's how I would have done that problem. Just want to show the work for it being a little different. Number 64, you may have multiplied by negative I, which would have gotten you -2I plus 3I squared over negative I squared, which would have gotten you a positive 1 on the bottom, and then -2I minus 3. So -3 minus 2I divided by positive 1, or just -3 minus 2I. Multiplying by positive I gets the job done too. Here's 66 and 68. I'd definitely be willing to go over 1 or 2 of these if we'd like to, because we didn't really hit a lot of the division ones. But there's the work for it. Basically, the process is the same for all of them. You multiply the numerator and the denominator by the complex conjugate of the denominator. So you're taking the negative or the positive inside the complex and switching it. So -1 minus 5I turns into -1 plus 5I, and you multiply that. Don't forget the FOIL on top and bottom. I mean, number 66, you don't really need a FOIL, but 68, you definitely do. I don't care if you split the fraction or not. Doesn't matter. Okay, let me take, yeah. There's 90 and 92. Again, I'm going to show the work a little differently for 94 and 96, but those are the correct answers. But again, yeah, I'm going to show the work very different. Like for me, did we just do I to the 11th? I to the 11th, that was like I to the 3rd, right? Which is negative I. Positive 1, positive I, -1, negative I. So really, this is just like saying 3 minus a negative I. So that's just 3 plus I. See that? In that respect, that's a lot easier, a lot cleaner than trying to make it even, like that whole, that's how we kind of used to teach it. Then we learned when we kind of not discovered, like we just kind of learned how to teach it with that mod 4 thing. 96, same kind of thing there. You would take 35 divided by 4. That'd be a remainder of 3. Whoa, what the heck? So this is going to act like I to the. Why does that happen? Like, I would love to know why when I scroll and then I try to write, see, but it's only sometimes. I know, am I bugging out? And then 24. 24 is divisible by 4, right? So this is going to act like I to the 0. And then I to the 18th, well, 18 divided by 4 is 4 remainder 2, right? It'd be like 4.5. So remainder 2, that's going to act like I squared. So this is like negative I minus 1 plus a negative 1, right? So negative I minus 2, or negative 2 minus I. Let me scroll down here for numbers 98 and 100. Again, you might have multiplied by a negative I, because that's truly the conjugate, and that would have gotten me a negative 18I plus 3I squared over negative I squared, which turns out to be positive 1 on the bottom, right? Negative times negative 1 is a positive 1. And then, so this turns out to be negative 18I minus 3, or negative 3 minus 18I in true A plus BI form. Yeah?
Okay, so why don't you giving it like, instead of negative 3 minus 18I, just negative 9?
That's okay. You're still getting the same numbers, but all the directions say leave your answer in A plus BI form. So you're right with all the numbers. Just put it into real then imaginary complex form. Any other questions that we'd like to talk through or go over? No? Okay. Let's do section 5. That was it, right? Just do 100. Mm-hmm. There we go. There we go. All right. So the last section that we will do here is curve fitting with quadratic models. Curve fitting with quadratic models. Remember back in the day, back in chapter, oh shoot, I don't even remember what chapter it was, chapter 2 maybe, we did lines of best fit, right? We had a table of values and we plugged them in our calculator and we figured out what the line of best fit was. We do that same thing. But like today, what we're going to be looking at today is like, okay, we know in our world, not everything is linear. You know, things in nature turn out to be like if I collected data and the plot and the points came out to look like that, would I really want to use a line of best fit? No, I would want to figure out some quadratic that matches that data, right? I don't know what type of scenario this would be, but it happens from time to time, okay? So what we're going to be looking at now and in the future are different ways that data can come out to be, and then the different functions that we could try to match to it, right? Today, we're going to talk about quadratic models. Now, so basically the goal for today is taking different things and making a quadratic out of it, okay? Taking different pieces and creating the quadratic, okay? Recall that you can use differences to analyze patterns in data. For a set of ordered pairs with equally spaced x values, a quadratic function has a constant non-zero second differences. So let me show you what I'm talking about here. Take a look at our original function, original parent function, f of x equal to x squared, right? Those are just points for x squared. I've got negative 3 all the way up to positive 3, just squaring the x values. Take a look at our first differences. Remember back in linear functions, we said, okay, if it's got a constant change in x and a constant change in y, then it's going to be linear. It's got the same slope, right? For quadratics, that's not necessarily true, right? It's not true. It's just not true. We would have a difference of -5, a difference of -3, a difference of -1, difference of +1, difference of 3, difference of 5, right? In a quadratic, this is going to happen. Look at the differences within the differences. Going from -5 to -3, I go up 2 units. -3 to -1, I go up 2 units. up 2 units, up 2 units. I find a pattern within the differences. This is going to be true throughout the rest of the year. If there's no pattern within the second differences, then it's not quadratic, but it could be cubic. I just keep finding the layers of differences, as long as I have enough data to do that with. Okay, if it's first differences, then it was linear, right? If this was a constant here, that was linear. If I do the differences again, and it's constant, same number throughout, then it's quadratic. If it's not there, I could keep going to see if it would be cubic. And then if it wasn't constant there, I could keep going to see if it would be quartic. And then so on and so forth, as long as I had enough information. For our purposes here, we're just going to stop at second differences and say, is it quadratic? Is it not quadratic? Are these the same? Are these not the same? Okay, so these are what we call a constant second differences. Second differences. So let's take a look here. Determine whether the data set could represent a quadratic. Could. Now we notice that the x values are equally spaced, right? So let's take a look at the y values. The y values. The y values are going up by 2, up by 6, up by 10, up by 14. So obviously, say this is not linear. I would have a constant first difference as if it was linear. So let's check quadratic. I go up by 4, I go up by 4, I go up by 4. Is this quadratic? Yes. So we say, yes, this could be a quadratic. It could be a quadratic because the second difference is a constant. Why do I say only could be? Because honestly, this is just a snapshot from 1 to 9. Could it do something really funky past 9? Sure. You know, or left of 1? Yeah, I guess so. But this is just a little picture of what's happening between 1 and 9. All right. X values are equally spaced. Let's take a look at the pattern in the y values. Okay, well, I'm going up by 2, up by 6, up by, what's the difference between 27 and 9? 18. Going up by 18. The difference between 81 and 18. 63, oh, sorry, 81 and 27. 81 minus 27. 54, there we go. So I'm going up by 54, right? Obviously, this is not linear. Let's check to see if it would be quadratic. I'm going up by 4, up by 12. They're between 54 and 18. 36. Is it quadratic? No. I could have stopped at 12, right? I saw 4 and then 12. We know that it's not quadratic. We don't know what this thing is, but at least it's not quadratic. We'll learn later on in the year that this is actually exponential because I see a pattern. Look at my y values. What am I multiplying by each time? Not adding, but multiplying by 3. Whenever you see a constant multiple instead of a constant difference, that's an exponential instead of a polynomial like we have. Just as 2 points define a linear function, we can actually do 3 points to define a quadratic. Okay, remember back in geometry when you said, okay, if any 2 points out in space are there, you could draw only one and only one line to go through them. We can extend that to 3 points to define a quadratic. If you have 3 points out in space, I guess it's say on a plane. If you have 3 points on a plane, there's only one possibility of a quadratic going through them, as long as those 3 points are not on the same line, non-collinear. Okay. Oh yeah, non-collinear. So let's do that. Now this process is going to use our graphing calculator. So if you do not have that, you might want to do that. I mean, the next thing that we're going to do too is going to use the graphing calculator. Well, so I say, here are my 3 points. Give me the quadratic that goes through those 3 points. This is like equivalent to being like, okay, here are 2 points. Give me the line that goes through those 2 points. Well, you had to find the slope, you had to find the y-intercept, and go through all that process. There's a method to doing this that uses something that we already know how to do. Let me go with this. We know standard form is ax squared plus bx plus c is equal to y, right? That's standard form. Ax squared plus bx plus c is equal to y. So if I could only somehow figure out a, b, and c, if I could only figure out a way to find a, b, and c, I'd be good. Here's how we do that. Let's take our first point at 0, negative 3. Okay, let's take our first point at 0, negative 3, and let's find the equation that matches that, meaning I'm going to plug in 0 for x, a times 0 squared plus b times 0 plus c is equal to the y value, negative 3. Again, all I did was plug in 0 for x and negative 3 for y. Let's do that same thing for 1, 0. Okay, a times 1 squared plus b times 1 plus c is 0. Same thing for 2, 1. A times 2 squared plus b times 2 plus c is equal to 1. Okay. So what we want to do is create ourselves. Let's reduce this down a little bit. And I know it's going to be weird, but I'm actually going to leave the zeros in. I know you could say like just c is equal to negative 3. I get that. But here's what this is going to be. 0a, I'm going to bring the numbers out in front of a, b, and c, plus 0b plus 1c is equal to negative 3. Yeah, I know. It's just c. But I'm going to write it like this for our purposes here. 1a plus 1b plus 1c is equal to 0. 4a plus 2b plus 1c is equal to 1. And you know what I just created? A system of 3 by 3 equations. But you may be thinking, oh my God, we got to do elimination or whatever with this. No, we know a better way. Remember right at the very end of that chapter 4, I taught you how to use matrices to solve something like this. Let's go through that process again. We're going to solve this 3 by 3 system using matrix equations. What does that mean? I'm going to take my coefficient matrix, 0, 0, 1. This is why I left the zeros and the ones there. 1, 1, 1. 4, 2, 1. I'm going to multiply it by now x, y, and z. Actually, no, a, b, and c, excuse me. Because my 3 unknowns are a, b, and c. And set it equal to negative 3, 0, 1. Okay, that means now all we're going to do is go in our calculators. This is a times x is equal to b. So to solve this, all I want to do is take a inverse times b. Okay, let's plug what we know in. I go back into matrix. Remember, matrix is right here. This is a good review for exams as well, right? Because we're going to need to do this on our exams. Here's my matrix button. Scroll right twice to edit, and I want to change A into a 3 by 3 matrix with entries 0, 0, 1, 1, 1, 1, and 4, 2, 1. I want to go back into matrix B. I want to edit matrix B into a 3 by 1 with entries negative 3, 0, and 1. Okay, now I go back out to my home screen. Remember, back out to the home screen. Get out. Back out to the home screen. And now I want to do A inverse B. Matrix A inverse matrix B. What is that telling me? That's telling me that A is -1, B is 4, and C is -3. -1x squared plus 4x minus 3 equals f of x, or f of x equals that. Let's write it that way. Do I really need the -1? No, I can just write -x squared if I wanted to. But that's your A, B, and C values. Can we do that again? Is there another example of that? On the back, yeah. B on the back. Let's do that process again. -4, 12, -2, 0, and 2, -12. All right, so that means -4 comma 12 is going to get me, remember that it's A times x squared plus B times x plus C is equal to y. Right, I'm plugging -4 in for x and 12 in for y. I do the same thing for -2 comma 0. So it's A times -2 squared plus B times -2 plus C is 0. And for 2 comma -12, that's going to get me A times 2 squared plus B times 2 plus C is -12. Again, all I'm doing there is just taking the 3 points, plugging x's in for x, y's in for y. Now, be careful here. Watch out. When I go to square, see, I need to evaluate these squares, right? To get what my numbers should be in the matrix, I need to evaluate all of these squares. So that's going to get me 16a minus 4b plus, and I like to put a 1c there, is equal to 12. This one's going to be a positive 4a minus 2b plus 1c is equal to 0. And this is going to be a positive 4a plus 2b plus 1c is -12. And that's my system. Questions about creating the system? Okay, so my matrix is 16, -4, 1, 4, -2, 1, 4, +2, 1, times A, B, C, 12, 0, -12. Now we run the numbers. Go back into matrix A. It's a 3 by 3. 16, -4, 1, 4, -2, 1, 4, 2, 1. Notice that my last column is always going to be 1s, right? Am I ever going to multiply C by X? No. C is just going to be sitting there as a constant the entire time, no matter what coordinates I get. So 1s are always going to be down the last column. Okay, so I go back in. I got to do my constants now. A 3 by 1 as 12, 12, 0, and -12. All right, and then we quit out back to the home screen. Remember, you always got to go back to the home screen before you do A inverse B. So I go matrix A, inverse, matrix B. Is that what you guys got? So that means that this is a f of x is equal to 0.5x squared minus 3x minus 8. That's the quadratic that runs through those points. And it's a perfect fit, right? I'm not saying that it's a close fit. I'm not saying that that quadratic ends up like really close to those points, just close enough. No, I'm saying that this runs perfectly through those three coordinates. Okay. Let me go back to what I was talking about at the beginning of the day today. Does it always in nature, in real life, run perfectly through? No, right? So we're going to have to figure out some way to see, okay, if it doesn't run perfectly through, how do we do that then? Well, that requires the quadratic regression, okay? A quadratic model is a quadratic function that represents a real data set. In chapter 2, we use linear regression. Now, remember that white, was it like a blue sheet of paper? Something, a linear regression sheet with all of like the screens. I can't remember what color it was. But I linked it into Canvas on this assignment as well. So if you want to see it, or want to print an extra copy, it's there. What I'm talking about here is, actually, you know what, I bet I have Canvas still up. Yeah, here. This is the sheet that I am talking about, the linear regression instructions. What's that? Was it just one? Yeah. Sometimes I print it in color, sometimes I don't. This thing, remember this thing? Yeah. So that's what I'm talking about here. That's linked into Canvas. We're going to be using that exact same process. You're going to be surprised at how much you remember. Okay? Remember talking about the R value? How it was a really good fit or not a good fit? What we're looking at now is what's called the R squared value. An R squared value is just an even better picture of how good the data fits, or how good the model fits to the data. Okay. The good part about R squared is that it's always just going to be positive now. There's no positive or negative to think about here. Positive and negative, remember, meant the slope of the line of best fit. For a quadratic, since there's not really any slope, we don't have to worry about positive, negative. All right, so let's do this one. This table shows the prices of, prices of wading pools. Wading pools, based on the pool's diameter. Find a quadratic model for the cost of the pool given its diameter. Use the model to estimate the cost of the pool that would be 8 feet. So we got like kids' pools here. They're all circular. And these are the diameters. So I got a $20 pool, a $20, $25, $25, oh, sorry, $19.95, and $34.95. So let me remind you of the process. So if I want to go through and plug in this data, remember you start here at stat. You go stat, and then you hit edit. Now I think I've reset my calculator since this point. So I don't see any data in there, but if you had some data, what the heck is that? If you had some data in there, say I've got just a 5 in there, remember you go up to the top of the list, you hit clear and then down, don't delete. Hit clear, then down. So let's plug in our list 1, 4, 5, 6, and 7. That's your diameters. Let's plug in our list 2, 1995, 2025, 25, 34.95. 34.95. Okay. Double check you're entered in correctly. 4, 1995, 20. Everybody good so far? So here's what we do. We go back out to the home screen. And then I'm going to clear out my matrix stuff. And I'm going to hit stat. And I'm not going to go to edit, but I'm going to scroll right to calc. And then do you see choice 5 right below where linear regression is? Quadratic regression. Right there. Quad reg. Some of you may have to keep advancing through and hitting calculate. Oh, do you notice how I don't have an R squared value? Some of you guys do. I don't. I think I've reset my calculator, which means I need to go back in and turn on my diagnostic. Catalog, and then go down to D for diagnostic. Then you got to run it again. Oh, there it was. Okay, so let me go back and run that regression again. There it is. That's much better. I see my R² value. Ooh, so how good of a fit is this? Very good, right? Very good. So y is equal to, now this is the quadratic that fits this data, 2.41x squared minus 21.56x. I usually only go out to 100. Plus 67.64. That's the quadratic that models that data. Okay, it says use the model to estimate the cost of a pool that has a diameter of 8 feet. All right, so I need to figure out what the y value would be when the x value is 8. So here's how we do that. Remember, you go back into y equals. This is the weird and funky part. I'm going to clear out everything that's there. And I want to put my regression equation in there. Here's how we do that. Remember, vars is the button to hit here. Vars stands for variable statistics. Vars, scroll down to statistics. Hit enter on that. Scroll right twice to EQ to find reg EQ. And you have to start at your y equals to do this, right? You have to start at your y equals. Your screen may not look the same as my screen if you've got an updated version of the calculator. And now I'm going to hit zoom 6 because I don't know where my calculator was. I don't see anything, and that's reasonable because look at my y-intercept. 67. I've only got a 10 by 10 window. So I'm going to zoom and then step. Oh, that's right. I never turned on my plots. I'm sorry. I've got to go into my y equals. I never turned on the plot to see the data. Zoom stat wasn't going to do anything because I didn't put my statistics on the graph. So I've got to make sure plot 1 is on. Remember, you go to your y equals, you got to make sure your plot 1 is on. Now when I go to zoom stat, there we go. That's much better. I see my quadratic along with my coordinates. Now, if I want to know the cost when x is 8, all I have to do, remember, if it's a value, if it's an x value, you go second calculate value of 8. What's wrong? I got to zoom out. I don't see it on the screen, remember? So go zoom 3, enter. There's a bit of better picture. Second calculate value of 8. So how much should the pool cost if the diameter is 8 feet? $49.54. $49.54. Questions about that? I'm not going to worry about example 4. Yeah, I want to pass out your exam review and talk about it a little bit. I'm going to leave the video running while I do this, so everybody at home can hear this still. So your exam review is going to be due at different times. Different numbers are going to be due at different times next week. We're going to start reviewing for the exam on Monday. Okay? It's not too bad. The algebra 1 practice exam is a lot more lengthy. Okay, and I'm going to write this on the whiteboard too, but I want the folks at home to see it as well. On Monday, okay? On Monday, we need numbers 1 through 26 due. Okay. On Tuesday, I need you to have the rest of it done. Numbers 27 to 45. Okay. The exam is full calculator. Okay, the exam is full calculator. There's no portion without a calculator. So that kind of makes all the chapter 4 stuff pretty easy. Yeah, all the matrix stuff, pretty easy. There's no sections where you just get to use a regular calculator. Everything is full graphing calculator. Okay. Remember the extended response portion is going to be on the first day, on Thursday. The multiple choice portion is going to be due on, or not due on. We're going to do that on Friday of next week from today. Does that make sense? Okay. I'm going to stop the video. And this is the homework for tonight. Okay. There's no homework over the topic that we just covered. We're just going to do this as our homework because that's due on Monday. Cool. All right. So long, everybody at home. See ya.